Welcome in next episode. Today we'll discuss a bit of applications of metallic particles, metallic powders in different powder metallurgy methods, in particular in additive manufacturing. Spherical particles are produced with different methods. One of those is, for example, gas atomization, widespread and used for industrial applications. But if we're talking about R&D, scale of gas atomizers is often too large to diligently carry on research and early optimization. There, ultrasonic atomization have its benefits. For example, rePOWDER created by AMAZEMET is one of the most versatile tools there to use ultrasonic atomization and provides spherical particles as R&D tool. Spherical particles have their benefit. Those are especially important when we're talking about additive manufacturing methods where stable feeding and stable spreading over the powder bed is vital for quality and stability of the process. So, most of our customers and ourselves are within the field of additive manufacturing. Different technologies starting with binder jet, laser powder bed fusion and electron beam melting. We can fine-tune particle size to different methods, changing frequency. So, for example, 20 kHz is primarily used for EBM and DED applications, while higher frequencies are predominantly used for LPBF and binder jet. Ourselves and our customers use mostly 40 kHz, which is our standard frequency used for LPBF technology. There, the main advantage of rePOWDER and main perk of our technology is capability of creating new alloys that are optimized for additive manufacturing. It's mostly used as an R&D tool to optimize chemical composition and get new improved properties for those processes. So one of the advantages of powder produced via ultrasonic atomization in rePOWDER is their very high sphericity. This sphericity translates to rheological properties of powder. The most important that we utilize in additive manufacturing is their free-flowing behavior. So it's easier to spread such powder across the powder bed. It's easier to feed it with different feeders, so the process of such alloy, processing such alloy can be smoother, and as a result, quality of printouts is higher compared to non-spherical particles. It's particularly important when we're dealing with new alloys where availability of such free-flowing particles is low. So there are several metal additive manufacturing methods on the market. The most widespread is laser powder bed fusion. There, we're spreading first powder across the powder bed, and later on it's molten with laser beam. Afterwards, they're layer by layer welded on top to create a final part. Their high sphericity of powder is vital for the process to be stable and prevent porosity with final part. Largest parts are produced via direct energy deposition. There are large elements up to a few meters can be processed. Also, coatings can be applied to existing elements or repaired. Here, spherical particles are important to provide stable flow for the nozzles, stable feeding, which is important to get a quality of the final part and prevent lagging of the machine. One of the technologies very similar to laser powder bed fusion is electron beam melting. There, instead of using laser beam, electron beam is used. A process is carried out in high vacuum chamber while the powder is preheated to prevent wrapping to reduce thermal stress. There are similar problems as in LPBF, so the powder have to be spread over the powder bed, but also it's vital to prevent so-called smoke effect. If electron beam is hitting the powder, it's being charged, and two small particles are very prone to be ejected from the powder bed. So preventing so-called smoke effect is one of the main challenges in optimizing electron beam melting process. One of the growing metal AM technologies is binder jet. Their process is indirect. a powder is not molten, it's only binded with special organic elements, and then it's removed from the machine and sintered within special furnaces. Their packing density is important for behavior, shrinkage of the final part. Getting spherical particles is important to increase packing density of such a green body that enables research over sintering behavior and shrinkage control. Metal IM is materials game. Getting most out of alloys for additive manufacturing is very important because those manufacturing techniques are considered one of the most expensive compared to casting or CNC milling. Designing new alloys is important research field right now in metallurgy, and it's important to use proper tools and proper powders for them. It's important to know that powder metallurgy is not only additive manufacturing. Actually, it's minor part if we compare total volume of parts produced with metallic particles. Emerging technologies such as hot isostatic pressing and spark plasma sintering also benefit from spherical particles. In HEP, filling of the capsule is vital to get proper net shaping. It's a pretty complex task to fill welded capsule and fill it completely with powder. There, high flowability and packing density is important to get high quality of near net shape part. In spark plasma sintering, dense element can be obtained with almost any powder, but it's critical to get proper chemical composition there, as it's kept during out the process. One of the expanding research field currently are high entropy alloys and intermetallics processed via SPS. There, getting pre-alloyed powder is vital for the final element, and getting them processed with, for example, mechanical alloying is a lengthy task that often limits research capabilities. There, getting spherical powders already in pre-alloyed form is a good tool to create swiftly new alloys via SPS. Yet, dense metallic coatings are mostly created with thermal spray. There, high velocity particles, either molten or in solid state, hit surface, and when they embed, they create coatings which are used for various technologies and research. There are two methods that we are using most there. First is plasma spray, the other one is cold spray. In plasma spray, the particle itself is molten in plasma jet, and in the molten state it hits the surface where it's embedded to create the final coating. In cold spray, on the other hand, particle is accelerated to supersonic velocities, and then in solid or semi-solid state, it is integrated with the base element. Both of those methods benefit from spherical particles. It's important to control feed rate in both of those methods, and it's vital that particles don't have too wide spread of their sizes. When processing a powder with wide particle size distribution in plasma spray, too small particles are already evaporated, while too large do not fully melt and cannot be embedded for the final base. In case of cold spray, particles are accelerated to supersonic velocities, and when they hit base material, they are embedded already in a solid state. They are getting particles with narrow particle size distribution. It's important to control behavior of such powder within a supersonic jet. Spherical particles are not all about powder metallurgy. Sometimes getting dense element or getting coating isn't the final game. There are applications where powder itself is a product and can be used for research. For example, few of our customers in US are using spherical particles not as a feedstock for additive manufacturing or coating methods, but they are using those as elements. There are, for example, silicon or silicon-based systems are important for nuclear research. So spherical particles are perfect for all of the powder metallurgy methods, right? Not really. There are methods which are not taking any benefit from spherical particles. For example, if we considered classical sinter and press powder metallurgy methods, using spherical particles is sometimes a big trouble. There are methods where spherical particles are actually inferior. For example, press and sinter methods require non-spherical particles to create decent strength of green body. It's much easier to press non-spherical particles and enable them to be interconnected compared to spherical particles, especially if we're talking about hard and non-ductile materials. From medical to nuclear research, spherical particles enable researchers to develop new applications, new alloys, and progress with material science. Thank you so very much for listening. This episode we discussed different powder metallurgy methods, in particular metal AM technologies. Next episode we'll discuss in detail features and parts of rePOWDER, ultrasonic atomizer created by AMAZEMET.